Hello and welcome to this topic, which is the first topic of the A2 part, or the second year of OCR A Level Chemistry. This one is how fast, which is essentially the rates of reaction. It builds on from topic 12, which was called reaction rates, and we're going to use a lot of the information that we had in that topic in this topic, including the graphs and including this rate equation, which says that the rate of a reaction is the rate of change of the concentration of either the reactants or the products. So if you need to, take some time now, look at that topic 12 about rates and then come back. Now the first part of the A2 specification of this says you need to know what all of these words mean. And a lot of them will be new, some of them are old. So the rate of a reaction, we already know that the rate of a reaction is the rate of change of the concentration of the products, or the reactants. And you've probably come across the word half-life before in GCSE physics to do with radioactivity. And it has the same meaning here, but instead of being the time it takes for half of a radioactive sample to decay, this is the time it takes for half of a reactant to react, or the time it takes for the concentration of a reactant to decrease to half. For all the others, so orders of reactants and overall order, the rate constant, and then we'll get onto rate determining step later, we need to talk about something new, which is the rate equation. And to do that, and to explain these in full, I need to dispel a few myths. And that myth is that concentrations always have an effect on the rate, or that if I double the concentration, I always double the rate. And these things just aren't true. We need to be a bit more specific in the A2 and talk about actual numbers. Rather than just saying increasing the concentration increases the rate, we need to put a number to that. And that's where it gets a bit more complicated, and that's where we need the rate equation. And the rate equation says exactly how each of the reactants change the rate of a reaction. So, for instance, in some reactions, when you double the concentration of a reactant, it doubles the rate. But sometimes when you double the concentration of a reactant, it quadruples the rate, so times it by 4. And sometimes when you double the concentration of a reactant, nothing happens to the rate, it stays exactly the same. And that's the new thing we've got to talk about today, and we call that order. So the order of the reactant. If when you double the concentration, nothing happens to the rate, we call that zero order. If you double the concentration of a reactant and the rate doubles, we call that first order. And if you double the concentration of a reactant and the rate quadruples, we call that second order. And that's also true for times it by 3. If I triple the concentration and that has no effect on the rate, that's zero order. If I triple the concentration and the rate triples also, that's first order. And if I triple the concentration of a reactant and the rate increases by a factor of 9, then that is second order. And hopefully you can see that those relationships are an exponential relationship, and the order is the same as raising to the power of. So when I said I tripled the concentration, if I raise 3 to the power of 2, because I said it was second order, then the rate will go 3 times 3 times faster, which is 9 times faster. And so the concentration of some reactants has more of an effect on the rate than other reactants. And some reactants have no effect at all on the rate. And the only 3 you need to be able to do are zero order, where it has no effect, first order, where it's directly proportional, and second order, where if you increase the concentration by a factor, then the rate increases by the square of that factor. So you might have more than one reactant. One of those reactants might be first order, and the other reactant second order. Those are the orders of the reactants. The overall order is the sum of all of the orders of the reactants. So if you've got 2 reactants which affect the rate, one of them is first order, one of them second order, then the overall order would be 3. And when you combine all of this information together, that gives you the rate equation. And so I'll give you an example of that. So this is just a generic example with 2 reactants, A and B. The lowercase a and the lowercase b, those are the orders of those reactants. So it could be a 1 for first order or a 2 for second order. You can see that it's squared. So if I have a doubled concentration, then the rate will go up by a factor of 2 squared. The overall order is just the sum of each of the orders of the reactants. So in this case, A plus B. But the rate isn't necessarily equal to exactly A to the power of lowercase a times by B to the power of lowercase b. It's very often different by a certain factor, and that is called the rate constant. So some reactions are really, really fast, some reactions are really, really slow. It doesn't matter how high the concentration is, some reactions just are slow. So rusting, for instance, the reaction of iron with oxygen, the concentration of oxygen in the air is pretty high, and the concentration of iron in iron is, let's not talk about that. But that reaction has high concentrations, and yet rusting isn't a fast reaction. And that's because the rate constant for rusting is much lower than the rate constant for burning, for instance, or combustion. And we'll talk about K later, but K is the rate constant. The rate constant contains all of the other things to do with rate, such as temperature and activation energy, or the orientation of the chemicals. Do they have to be a very specific orientation to react, or can just bumping into each other make them react? That's all involved in K, the rate constant. And we'll talk about that later, as I said. Everything else is the concentrations. And you'll get a lot of questions about how concentrations affect the rate of a reaction and determining this rate constant. And so it's worthwhile talking about those questions and how do you actually determine the rate constant? How do you determine the orders of the reactants? And there's three main ways that happens. Two of those ways are graphs, and one of them is just tables of data. So I'm going to give you some examples of those so you can get to grips with how to write a rate equation. Okay, so these are the easy graphs in my opinion. They plot rate against the concentration, and then if the concentration doesn't affect the rate, then we call that zero order. If it's directly proportional, so the rate and the concentration, as one doubles, the other one doubles, then it's a straight line starting at the origin. And if when you double the concentration, you quadruple the rate, or triple the concentration, you increase the rate by a factor of 9, then you end up with this parabola, this x squared graph. 0, first and second order. There's a slightly more difficult graph that you might get, and I showed you one in the last topic, so the topic 12 one. I'll draw those up now for 0, first and second order. And these are those graphs. So it's a concentration against time graph. If you remember, the rate of a reaction, we worked it out last time by drawing a tangent. The rate of a reaction is how quickly it is going down, so the gradient. You can see this one is going down, and the rate isn't changing. So the gradient of this line isn't changing over time. So the concentration of this has no effect on the rate of that reaction because the gradient doesn't change. In this one, you can see the gradient gets shallower and shallower, which means that the rate is going down and down. This one, as the concentration of B decreases, the rate decreases. This one specifically has a constant half-life. The bottom one you don't actually need to be able to recognise. I've just put that there for comparison purposes. It looks very similar to the one for the first order, and that's why you don't need to be able to compare them. This one actually has a half-life which increases over time, and that's why you don't need to know it. Just the first two, so zero order and first order for those graphs. And the other way you can be asked to do this is with tables of data. So they'll give you concentrations of A, B, and C, for instance, in this reaction, at the beginning of a load of different reactions. They'll tell you the rates of all of those reactions, and then they'll slowly change the concentrations. And when they do that, what you've got to look for is the changes. So if, for instance, B and C stay exactly the same, but A's concentration doubles, you look at what effect doubling A's concentration has on the rate. And if the rate stays exactly the same, then that's zero order. If the rate also doubles, then it's first order. And if the rate quadruples, then you know it's second order. So in this case, if we're talking about this A, then the rate would stay the same. And from that, you'd know that the concentration of A has no effect on the rate, so A is zero order. For B's data, it's first order, and so if they double the concentration there, then the rate would double. Equally, if they halve the concentration, the rate would halve. And then for C, if they double the concentration of C, then the rate would quadruple. With those, you have to make sure that only one of the reactants' concentration is changing. Otherwise, you can't compare them. Sometimes they'll give you data where that's not always true though, but one of them you can find out. So look at the data, and a lot of the time you'll be able to calculate one of them, so that you know that, for instance, A is zero order, and then they'll change A and B in the next experiment. And so you know that A has no effect on the rate, so any rate change will be due to B's concentration changing. The only way they can not do that is if, for instance, they give you one of these graphs, and you determine that A is zero order from the graph, then they can change A in all of those. And you have to be able to realise that A has no effect on the rate, and so it doesn't matter what A says, you only look at B and C. Now there's one special circumstance we need to be aware of, and that's if the overall order of the entire reaction is 1. If that's the case, you'll end up with a graph that looks like this, and when you've got that, That's the only reactant that makes a difference, and it's first order. You can work out the half-life of that and use the half-life to calculate the rate constant. And in that case, the rate constant will be equal to the natural logarithm of 2 divided by the half-life. But that's only for a first order reaction, and it's only when you've got a concentration time graph with that reaction. So if you're not a mathematician, this natural logarithm is on the calculator. Just press ln2 and then divide it by the half-life. Hopefully you've seen that calculated before. So just take half the concentration, go across, and then whatever time that is, that's your half-life. On my calculator, the ln button is just there. So you just press ln2, close the brackets, and then divide that by whatever the half-life is. Say it's 1 second. Then that's your rate constant. So for every other reaction which isn't first order overall, you need to use the rate equation. So that's this rate equation here. You'll be given a bunch of data, including the rates and the concentrations of all of the reactants. You just pick one of those experiments, put in the rate and then the concentrations raised to the correct powers, and then K is the only unknown left in that equation. So you just do rate divided by all those concentrations raised to the correct powers, and that gives you the rate constant. So let's talk about units very quickly. Rate has the units of moles per decimeter cubed per second. Each of your concentrations will be in moles per decimeter cubed. And so you can work out the units for the rate constant by doing the units of the rate, which is moles per decimeter cubed per second, divided by the units of all of your concentrations times together. So for instance, in a third order reaction, you do rate, which is moles per decimeter cubed per second, divided by moles per decimeter cubed, divided by moles per decimeter cubed, and divided by moles per decimeter cubed again. You end up with mole to the power of -2, and then decimeter to the power of 6. Don't forget the per second, because rate has a per second, therefore the rate constant must be per second. So that would be moles to the power of -2, decimeters to the power of 6 per second, or seconds to the power of -1. I'll just write that out because that's a lot of numbers and minuses to hold in your head all at once. Now, if you're a physicist, then you've probably seen these all before. You'd probably put the decimeters cubed at the beginning because it's a positive power, but this is fine for chemistry. If you're a non-physicist or non-mathematician, whatever the order of the reaction is, the overall order, that's the number that goes here. So all I've done to get from this side to this side is this number 1, because it's moles to the power of 1, -3, gives you -2. -3 minus -3 3 times is -3 minus -3, which is 0, minus -3, which is 3, minus another -3, which is 6. That's where the 6 comes from. And then this per second, there's nothing on the bottom, which changes that. So that becomes per second. If that still doesn't make sense to you, then feel free to ask questions in the comments below. Or if you've got a friend who does physics, unit analysis for physicists is like bread and butter. So make sure if you can, you can ask one of those. Now I said I would come back to this rate determining step, and here it is. Some reactions take place over more than one step. We've already seen some of them, like the free radical substitution mechanism has many steps. And the rate is only determined by the slowest of those steps. So if you imagine lots of reactions all happening at once, say there's a really, really fast one, followed by a fast one, followed by quite a slow one, and then the faster one again. It's the slow step, step 3, which is going to determine how fast that reaction happens. So I'm going to come back to this one. So this is a reaction between A and B. And so let's just give a basic example. It could be 2A plus B makes C plus D. Now it's possible that this all happens in one step, where 2 A molecules collide with a B molecule and make C and D. But it's also possible that it happens in more than one step. And the way you can kind of investigate how this mechanism works is by using the rate equation. And the rate equation tells you what happens in the slowest step. So if, for instance, the order of both A and B is 1, that tells you that in the slowest step, there's 1A and there's 1B. And they collide to make something. We don't know what it is, and you can't tell normally, but we do know that that slowest step just involves 1 A molecule and 1 B molecule. And let's say that that slowest step is the first of 2 steps. And questions go like this. So the question might say that it's a 2-step process. The first step is the rate determining step, and this is the overall equation. You've just determined the rate equation, and so it asks you to just suggest what the two-step mechanism might be. And if you know that A and B are both first order, then the slowest step is just A plus B. Now you don't know what that makes, but you don't need to. This bit here, taking the rate equation to write the first rate determining step, gets you a mark. As long as what's written on this side balances with what's written on this side. So I'm just going to say that makes E. Obviously in the question it will give you actual chemicals, and I'll cover that in a second. But the basis, you can just add them together to make E. So as long as E contains all of the atoms from A and B, then it balances. The next step of the two-step process has to make C and D, because there's only two steps, and the products are C and D. It also needs to use up E, because there's no E as a product, and so E must be an intermediate. And the final thing it has to do is include another A. So far I've only used one A in this, and it says in the overall equation there's two A's. So the next step must be E plus A makes C plus D. So now I've used up this E, so it's no longer there, and I've got two A's being reacted with one B to make C and D, and that's exactly what it says in the overall equation. In fact, if you just add together the left-hand side and add together the right-hand side, and then cancel out anything that's the same, you end up with that exactly, and that's how you know you've got it right. And there's some classic examples. I'm just going to go through one of those. So nitrogen dioxide reacts with carbon monoxide to make carbon dioxide and nitrogen monoxide. And the rate equation for this reaction is this, that nitrogen dioxide is second order. And let's say that it's a two-step process where the first step is rate determining. So here RDS just means rate determining step, and that's the first step. This is the slow one. Sometimes you'll see this written as slow and fast. I've just written RDS to show us that that's the rate determining step. And the rate determining step, to work out what the reactants are in that step, you just put in the reactants from the rate equation. So here I've got two nitrogen dioxides, and so here I write two nitrogen dioxides. Now it doesn't matter particularly, not on the mark scheme anyway, what you'd write here. So what I suggest most of the time, almost always, is just add them together. Whatever the thing is you've got on this side, you need to just add it together. I could write N2O4 there, and everything would be fine. That would work out perfectly well, and you'd get all the marks. But the way it probably works is by making this nitrogen monoxide. It's one of the products, so I might as well put it in on this side. As I say, it doesn't matter what you write there as long as it balances with this, and as long as you use it up in the next step. But I can make one of the products, so let's make one of the products. This NO3 is nowhere to be seen, and so has to be used up in the next step. But what does it react with? Now we've already used the nitrogen dioxide. In fact, we've used two, so we need to keep that in our minds. We haven't used a carbon monoxide, so that's another reactant that needs to be used. So I'm going to put that here. Now, maybe because I already know where this is going, I can see what's made. It has to be the carbon dioxide, because we haven't yet made the carbon dioxide, and this is the end of our reaction. So we have to make carbon dioxide. And the other thing that's made, once you've transferred an oxygen to that carbon monoxide, is nitrogen dioxide. And that one nitrogen dioxide is going to be one of the two that reacts in the first step. So I'll add them together at the end so you can see what's happened. If you add together reactants on the left-hand side and you add together the products on the right-hand side, that should give you, once you've cancelled everything out, the overall reaction. So let's just do that. And hopefully you can see now that if I cancel out everything that's the same on both sides, so this nitrogen trioxide and this one, and then I've got two nitrogen dioxide here and then one over there, so if I get rid of that and the two, then that just gives me back the original equation. NO2 plus CO makes NO plus CO2. And that's the overall equation done. So the things that you know have to be true. You know that this has to be two NO2s reacting together with nothing else, because that's what the rate equation tells you. And you also need to know that if you add step 1 and step 2 together, you end up with the overall equation. And that has to be true too. Every other part of it is just making sure that you've reacted everything that's on this side, and you've produced everything that's on this side, and that the whole thing balances out. Now the last thing we've got to go through is something called the Arrhenius equation, and it's all to do with this rate constant K. So we'll get rid of all this and then draw up the Arrhenius equation. Now I don't want to go into a lot of detail about the Arrhenius equation, because if you are a mathematician, then you've come across E before, so I don't need to tell you about it. And if you're not a mathematician, if I talk about E, then it's just going to scare you, and you really don't need to know that much about the Arrhenius equation. It tells you what affects the rate constant. So we already know that concentration affects the rate of things, and that's all in the rate equation. But we know that temperature also affects, and that wasn't included in the rate equation. That's because the temperature is in the rate constant, and we know that if you increase the temperature, the rate of a reaction increases, and so temperature increasing must increase K, because the rate increases, but the concentrations don't change, so it must be the rate constant which is increasing. And you don't need to be able to use this equation to calculate how much the rate's going to increase from an increase in temperature. You might want to have a go at it. If you know the activation energy and this A, which is the pre-exponential factor, which is just a number that they give to you, then you can calculate that. But you don't need to. It says in the specification that you need to be able to do a qualitative explanation, which is just no numbers involved. So increasing the temperature increases the rate constant, and hence increases the rate of the reaction. The only other thing you need to be able to do with the Arrhenius equation is use it to calculate activation energy when you're given a bunch of information. I explain how to use that. You don't use this form of it, you use the form when you've found a natural logarithm of both sides. Again, you don't need to be able to get from this to the other form, and actually you don't need to remember either form because they're given to you on the data sheet. All you need to be able to do is use that other form to plot a graph to calculate activation energy. So you might want to do this if you're a math student. Find the natural logarithm of both sides and see if you can make it equal this equation. And I've written that equation in this form because we're going to plot a straight line graph with it. And straight line graphs always follow the y equals mx plus c that you learned at GCSE. And what we're going to do is plot ln k as y and 1 over t as x. So I'm just going to rewrite this slightly to show you what I mean. So if you think back to GCSE maths, we're going to plot ln k on the y-axis, 1 over t on the x-axis, and then the gradient of our line is going to be minus EA over r, so it's going to be a negative gradient, and the y-intercept will be the natural logarithm of a. I have seen questions where they ask you to calculate 1 over t. You just do 1 divided by the absolute temperature. Find natural logarithm of k, that's the ln button I showed earlier, and then whatever the value of k is. And then you just plot that on a graph of y against x, or ln k against 1 over t. And you end up with a negative gradient graph, and you end up almost always with these below 0. This point up here, where the line intercepts the y-axis, will be the natural logarithm of the pre-exponential factor. Very rarely do you have to do anything with that. What you almost always have to do if you've plotted this graph is calculate the activation energy. So for that, we're going to need to know the gradient of the lines. So you just find 2 points and measure the change in y and divide that by the change in x. That calculates your gradient. And we already know that that gradient is equal to minus the activation energy divided by the gas constant. So to calculate the activation energy, all you do is take the value for the gradient that you worked out, it should be negative, and then times that by minus r. Now, in my experience, most people will forget that the gradient should be a negative number because it's going down, and this gradient will be a positive, and then they times it by minus r, and you end up with a negative activation energy. Now, obviously, negative activation energy doesn't make any sense. Your answer to this whole thing should be positive. So if you just want to find out the gradient as a magnitude, and then multiply it by r, then that's fine. Your activation energy will come out as joules per mole. And really try not to overthink this. It's very easy to because of the complexity of the equation. But the only questions I've seen so far is a graph has been already pretty much drawn for you and you just need to work out a couple of values and draw a straight line. Calculating a gradient, although the numbers might be different to the ones you've seen before, it's a GCSE skill. It's just determine change in y, change in x, and divide change in y by change in x. All you've got to do after that is times that number by the gas constant, and you end up with your activation energy. Now, there's a couple of steps there, but nothing overly complicated. It just is stuff that you probably haven't done in a while, especially if you don't do maths. And this equation, as written, is very confusing for a non-mathematician. So just follow those steps, work out the gradient, times it by r, and there's really not much else to do. And actually, that's the end of the whole of this rates topic for how fast. Thank you very much for watching, and I hope you can join me in the next one. Goodbye.